Okay. Right. Let me just check my sound. Okay, that seems fine. Well, hello everybody. Hello. Oh, hello Physicso. Nice to see you. Right, okay, I was just sorting out my sound there. Okay, so I found a couple of sort of neat little problems on Reddit again. There was a pretty cool one I got here. Well, I mean, it's not that cool, but I thought I'd talk about it because because somebody asked it online anyway. So this is a little mechanics problem. As I'm going along, feel free, as usual, to put any questions, comments, etc. in the chat. Hopefully we can just chat about some things. But first I thought I'd talk a bit about this problem here. So this problem talks about a parachutist that is jumping out of a plane, and they feel some air resistance proportional to v squared. And because it's proportional to v squared, I think that means that the air is moving turbulently over this person. I think generally if it's sort of laminar flow, it's proportional to just the speed. But if it's proportional to... Sorry, I just realised I need to adjust because I can hear my own background music coming through. And it's quite distracting. Okay, there we go, great. If it's proportional to v, then it means it's laminar flow. So because this is proportional to v squared, I think it's turbulent. So the first one is, hello as well, hello Tyrion 1803. So the first part is quite straightforward. They're just looking for us to find the units of alpha. So all of the units in an equation have to balance. So the units of the left-hand side have to be the same as the units of the right-hand side, and the units of this term have to be the same as the units of this term, and so on. Okay, so for part A, the units of mg, I put a square bracket to mean I'm finding the units of this thing. Well, the units of mass are kilograms, of course, and the units of g, the gravitational field strength or the gravitational acceleration, are meters per second squared. Okay, so these all have the units of a force, unsurprisingly. So that means also that the unit of alpha v squared must be kilogram meters per second squared, because all of the units on each side of the equation have to balance. And of course we know that the units of v squared are the units of velocity squared, so that is meters per second all squared, and that must equal kilogram meters per second squared. So we can rearrange this equation quite straightforwardly, and we end up getting, well, let's see what we get. We get a cancellation of the per second squareds here, and we get a cancellation of this mass and of one of these masses here. So we just end up with an m on the left-hand side. So the units of alpha are kilograms per meter. Okay, so that was fairly straightforward. Part B is where it gets a little more tricky. Well, part B is also okay. C is where it gets really tricky, but let's look at B. So we're imagining this parachutist falling out of the plane. The air resistance force on her is getting bigger and bigger the faster, the longer she falls for as she speeds up. And eventually this air resistance force will balance the force of gravity that is pulling her downwards. And the speed at which that happens is what we call the terminal velocity. So this is what we want to find out. She reaches terminal velocity when her velocity is at a maximum. So that is the definition of the terminal velocity. It's the maximum velocity while she's falling. So if velocity is a maximum, then you know that the change in velocity with respect to time has to be zero. That's sort of a thing we know from calculus. Or you can think about it in terms of kinematics. Your velocity is at a maximum when your acceleration is zero. Because if your acceleration wasn't zero, you'd either be speeding up or you'd be slowing down. Okay. So we have dv dt is 0. And if we look back at our equation, which was this, I'll write it down. That, straightforwardly, you can see, means that the whole left side of this equation must be 0. Therefore, we have mg minus alpha v squared is 0. And we can rearrange for the terminal velocity, which will be mg over alpha and all square rooted. Let me put that down there a bit neater. Okay. Then part C is where things get slightly trickier. So part C wants us to estimate how much work is done by air resistance as the woman falls. And they tell us that we can assume that she's falling near terminal velocity by the time she reaches the ground. So I'm going to do this two ways. I'm going to do it first I think the basic way they want you to do it, where they want you to just assume that she's travelling at terminal velocity by the time she reaches the ground. And then I'm going to do it a slightly more analytic way, and from that analytic expression we'll be able to derive when our estimation is good, when our estimation works well. Okay, which is always an important thing to do. If you make any sort of assumption or choice in your modelling, you want to be able to justify that and say when it is good. Terminal velocity when she hits the ground. Yeah, so, I mean, it's not a very good parachute, clearly. Yeah. I mean, she might as well just have not put the parachute on. Or, well, I suppose, unless she puts the parachute on the second she jumps out. If this alpha is modelled as the parachute, she's wearing it from the instant she jumps out, but yeah, you want to travel at a pretty low terminal velocity when you're hitting the ground, which is what the parachute does. The parachute will increase this factor alpha when she opens it. And if it increases the factor alpha, you can see here increasing alpha is going to reduce the terminal velocity. Because you don't want to be travelling, at the terminal velocity of a normal human without a parachute when you hit the ground. I mean, that would just make a mess. Okay, so we've got our equation from before. I'll write it down again. mg minus alpha v squared. So let's do a sketch of the problem. I'm going to call this upwards direction y. Here we've got the floor, which is at y equals 0. And here we've got the height that the parachutist jumps out from. So here she is, as soon as she starts jumping from the plane or the helicopter, whatever it is. And then some way down, she's travelling in general with some speed v. And we're going to assume that when she hits the ground here, she's travelling at the terminal velocity that we've calculated before. So I should draw this arrow bigger because the terminal velocity is the maximum velocity. So if we're drawing these things to scale, the terminal velocity here should always be bigger than the other velocity. Yeah. I mean, hopefully this is the parachute terminal velocity, or else, well, she's in a bit of trouble. We can, if we like after, we can think about what value of alpha this parachute should have such that she doesn't splat. Which is obviously the goal of a parachute, is to stop you from splatting. So, let's think about conservation of energy. So the total energy that this lady has is made up of kinetic energy and potential energy. So let's think about the total energy at the top before she jumps out of the plane, here, so at y equals h. Well, assuming she, doesn't throw herself at the ground, she doesn't sort of kick off away from the plane in a downwards direction, which is just, just asking for trouble, really. She's got no speed the instant that she leaves the plane. So her velocity is 0. So for kinetic energy, we've got half m 0 squared, just no kinetic energy. And then for potential energy, well, she has a height y equals h above the ground. So we'll measure our potential energy from the floor here. So that is plus mgh for her potential energy. Well, what about the energy at the bottom when she hits the ground? Well, the energy at y equals 0. Now, as the question has told us to do, we're assuming that she's at terminal velocity by the time she reaches the ground. So we're assuming that the height is large enough above the ground, where the plane is, that she's had enough time to accelerate to terminal velocity. So at the ground, she has half mv squared, where her v is now her terminal speed, and her kinetic energy, well, as we're measuring kinetic energy from the ground level, so we're measuring it in terms of heights above the ground, she has no height above the ground when she hits it, so she has mg times 0. Okay, so this is her total energy before she jumps out of the plane, and this is her total energy when she hits the ground. So where does the work done by friction come into all of this? So if there was no friction, the energy she has here would be exactly the same as the energy she has here. But because there is friction in the form of air resistance, this frictional force is taking energy away from the system. So of the energy she starts off with here, which we've written here, the work done by friction is subtracting from that energy to give us the energy she finally has at the bottom. Okay? So we write that down. We can say the energy she has at the top, oops, y equals 0. Oh, did someone, what's the word? Follow, that's it. Thank you, Blaman16. I keep getting mixed up between the word follow and subscribe. I can never remember which is the normal one, because the terminology is slightly different over YouTube and this. Oh, hello, Adam, altogether. Hello. Hello, Theoretical Phys 77. Thank you for following. So as I was saying, the energy that she has at the bottom is not totally equal to the energy she has at the top, because air resistance has taken away from that. It's done work to slow her down. It's done work to take energy out of the system. So writing this mathematically, that's a funny looking equals, we have the energy at the top minus W, where this is the work done by air resistance. And that is equal to the energy she has at the bottom. Okay? And now we can rearrange for W, of course. So W is the energy at the top minus the energy at the bottom. And now we can calculate this. So of course, here we have V is 0, so this is quite simply just mgh for the total energy at the top. And the total energy at the bottom, because she has 0 height, that is just half m terminal velocity squared. Therefore, the total work done is mgh, the energy she has at the top, minus half m vt squared, the energy she has at the bottom. Okay. And we know what vt squared is, of course. We calculated that a little earlier on. So we just put vt is root mg over alpha into what we were doing before. So from earlier we found this. So if we put that all in, we get the work done by air resistance is mg times h minus 1 over 2 alpha. So that's our answer. Well, this is our approximate answer. It's not an analytic thing, and we've not completely justified it. So I made a comment when we were doing this that said we've assumed here that she has terminal velocity when she hits the ground. But of course that's not necessarily true. You know, if I drop something from a foot above the ground, it doesn't reach terminal velocity by the time it reaches the floor. It has to have long enough to fall in order to reach that maximum speed. So what we can do now is we can be a little more careful solving this problem, and we can do it analytically, you know, using a little bit of calculus and integration, and then we can justify whether what we assumed before about her reaching terminal velocity is a good thing or a bad thing for a given height h. If it's a very large h, then it's probably pretty good, because then she'll have lots of time, you know, when she's falling from the plane to the ground to reach terminal velocity. But how large does h exactly have to be? That's what we want to justify. Okay. Oh, someone has asked a question about inflation, which I will get to after this. I won't interrupt my train of thought, but thank you very much, X11, Exaventian. Sorry, I don't think I said that right. Okay, so now let's do this slightly analytically. Okay. Anyone else in the chat that knows a little about cosmology and inflation, feel free to answer the last question there while I'm going through this, but there's no pressure if not. So analytically, let's look at the equation we have again. We have m dv dt is equal to mg minus alpha v squared. And I'm going to copy the diagram I had up here. But I'm going to change it slightly. So now I'm getting rid of this assumption that the lady is at terminal velocity when she reaches the ground. She'll have some final velocity, which will be less than terminal velocity, but we don't know how close to terminal velocity it is, etc. Theoretical physics says v dv dx. Well, yeah, that is the trick we're going to use to solve this. Very well preempted, but we'll talk through that in detail now. Okay, so our conservation of energy argument is still totally fine. So this equation we wrote down here is still totally all right. Except now instead of vt, we have the final velocity. It's not necessarily the terminal velocity, because we haven't yet justified how close to terminal velocity this thing is. So this expression here is still totally fine, but for changing this t to an f. So it is in general some final velocity we haven't yet worked out, okay? And now we want to work out that final velocity. So it's always important in these problems to specify, our initial conditions. So we know that at y equals h, the velocity is 0. And we have also that at y equals 0, the velocity is given by vf. And I'm taking the velocity in a downwards direction here. So my positive speed is downwards, because all my speeds are going down. I don't want to muck things up with that. But I'm measuring y in the upwards direction. So that'll have a slight subtlety when we come to write down v in terms of dy by dt. Slayer Darth says, Robin chat, how's it going? I'm doing well, thank you. I hope you're doing well too, Slayer Darth. Okay, so let's try and solve this equation. So Theoretical Phys 77 also pointed this out very nicely. So what we're going to do is, because our aim here is to find the velocity, vf, in terms of the height, y equals 0, having time here as a variable is not useful for us, because we don't know how long it takes for this thing to hit the ground. All we know is what height it falls through. It falls through a height, h. So we want to change this bottom variable here. Instead of being in terms of time, we want to change it in terms of height, or in terms of y, okay? So that is what Theoretical Phys 77 suggested. They suggested we use the chain rule to write dv by dt as dv by dy times dy by dt. And you can think of this in terms of cancelling of denominator and numerators, but it's technically not like that. And mathematicians get rather upset when you treat these things like fractions, because they're not fractions. The chain rule is a separate rule, and you have to prove it. You can't just say it acts like cancelling fractions. But this isn't a calculus talk, so we won't go into that. We'll just take that as a given, okay? So now we notice that dy by dt is pretty much the speed the thing is falling down at. It's the change in the height with respect to time. But because I've taken my height in the upwards direction and my speeds in the downwards direction, I'm writing dy by dt is minus v, okay? Which is important. That sign will have an important effect. So therefore, in full, dv by dt is minus v dv by dy. So this is a useful expression we've got for dv by dt. And now we want to put this back into here. we want to rewrite this equation in terms of y instead of in terms of t. So putting it into our original equation, we have minus mv dv by dy, and that's still all equal to the same right-hand side here. That's mg minus alpha v squared. And this is a separable differential equation. So let's write things a little bit nicer first of all. What I'm going to do is I'm going to divide everything by mg. And in doing that I get minus 1 over g v dv dy is equal to 1 minus alpha over mg v squared. Okay. Well, now I've got something that depends purely on v squared in terms of variables on this hand side. What is this chat saying? Okay, just chatting. Nice, cool. So this thing purely depends on v, and I want to bring it onto this side with the other things that purely depend on v. So that gives me minus 1 over g, v dv, and again, sort of seemingly haphazardly treating things as fractions, but it's okay, trust me. And then I'm also going to take this dy onto the other side. This is this separation of variables technique for solving differential equations, okay? And now just to polish things off, I'm going to times both sides by minus g to get rid of this term here. So this goes away, and I get a minus g here, okay? Well, now the standard technique is to integrate both sides, to get rid of these differentials. And now our initial conditions become important. So remember, we said that y equals h, or when y equals h, v is equal to 0, and when y equals 0, v is equal to this general final velocity vf. So let's put that in as the limits of our integration. So we have initially y is equal to h, so we put that down there. And then finally y is equal to 0. This thing starts off high and falls down low. And when y is equal to h, v is equal to 0. So I put a 0 here, and finally this thing is equal to vf. Okay, and now we run through the calculation. So this whole thing here is a logarithmic integral. You can trust me when I say that this thing is minus mg over 2 alpha, natural log of 1 minus alpha over mgv squared, evaluated at vf and 0. You can test it back if you like. That you're always best testing your integrals by differentiating back. So if I differentiate this whole expression here, for logarithms you take the derivative of the inside of the bracket as the numerator of a fraction, and that's all over what's inside here becomes the denominator. And the derivative of this gives us minus 2 alpha over mg. The 2 comes from here, and that should cancel this to give us what we have here. Okay, so that's all fine. And then on the right hand side we have minus gy evaluated between 0 and h. Okay, so on the right hand side that gives us gh. Now the minus cancels the kind of minus you get from here because this is a lower limit. Hello non-dairy neutrino. Sorry, I think I've missed a few things in the chat, but I think it's probably just chatter, so that's okay. I'll read it shortly though. And then on the left hand side, sorry, we've got, well, putting 0 in here for this lower limit, that gives us 1 minus something 0 squared. So this is going to be logarithm of 1, and logarithm of 1 is 0. So this whole thing is going to be minus mg over 2 alpha, natural log of 1 minus alpha over mg v final squared. Okay, And now the task is just to rearrange for v final squared. So you can already see that it is going to be different to the terminal velocity. In general, it will depend on how high we drop this thing from. Okay, so first we can just take this fraction here to the other side and take an exponential. So we end up with 1 minus alpha over mg v final squared is equal to e to the minus 2 alpha gh all over mg. So of course right away we can cancel these g's. So this simplifies quite a bit already. And then rearranging for vf will give us, you can just trust me here, or don't trust me, check it and point out if I make a mistake, is square root mg over alpha times 1 minus e to the minus 2 alpha h over m. And that whole bracket is square rooted, that square bracket. So you can see that when this term here is small, so Vf will approximately be mg over alpha when e to the minus 2 alpha h over m is much, much smaller than 1. Because in that case, you know, when this thing is very, very small, we basically just have the square root of 1. And the square root of 1 is, of course, just very near to 1. And if you remember, mg over alpha was precisely the expression we had for our terminal velocity. Okay, so that means we can write this expression for our final velocity as being terminal velocity times this factor 1 minus e to the minus 2 alpha h over m. And this thing is very close to the terminal velocity when this thing here is small. And this thing here is small when 2 alpha h over m is much, much bigger than 1. Okay. Well, sorry, is much, much bigger than 0, I mean. Okay. And that justifies what we were saying earlier about how this thing is very, very close to terminal velocity when this thing is very, very much bigger than 0. So when h is a very large number, this thing will approach terminal velocity pretty quickly. Okay. There was another question as well I saw, which was pretty cool. So, wait, so let me scroll up. Someone asked a question about the inflaton. So, Exaventian said, so the inflaton field is a scalar field according to the Friedmann equation and the requirements of inflation. This makes it bosonic. What sort of field would or did this interact with? Was it a totally free field? Well, to my knowledge, in sort of simple single field inflationary models, this thing is a field that it's coupled to gravity, but I think that's about it actually. So later on, as you get this kind of reheating, it does, the energy from this field does go into the standard model fields, but I don't think I think it only has a sort of simple coupling to gravity as far as I know. But there are lots of inflationary models, some that have multiple fields which are coupled to each other. But I think in the simplest case where you have sort of a single field inflation, as far as I know, that it's not coupled to anything other than gravity. I believe I'm correct in saying, but someone can correct me if that's not true. So there's some other stuff in the chat. You're talking about GR. Physics O doing a GR class, or you're done doing it now. Grad EM. Yeah, EM is one of my favorite courses. We did it mostly in second year undergrad, and then we did sort of covariant EM stuff more in third year undergrad, and then fourth year, like my master's year, we did QED, quantum-y, electrodynamic stuff. So it's nice having it built on pretty much every year throughout the degree. Okay, and Theoretical Phys 77 says, what was the most difficult year 1 course and which college would you recommend for physics? My most difficult year 1 course was probably either electromagnetism. Electromagnetism and optics was one exam at my undergrad university, and that was certainly the exam I did worst on, mostly because of the optics component. I'm really not a fan of optics. But probably the one that was the biggest jump up was probably linear algebra, which might have something to do with the lecturer that took it. I mean, he was a very good lecturer, but he was kind of a pretty hardcore string theorist, very pure, very sort of rigorous. Was it Lucas? Oh, it was Lucas. Yeah. How do you know Andre Lucas? Are you an Oxford physicist as well? But yeah, no, it was a really good course, but I think most people probably found it difficult just because it was very, hard going for a first year course. But I mean, it was very good to do, and he's a very good lecturer. Oh, you just read up on some lecture notes. Okay, yeah, his lecture notes are very good actually for that course. If they're accessible online, I would definitely recommend Andre Lucas's linear algebra notes for learning linear algebra. Then Examentian said, our QED stuff is in a separate class. E&M is just a repeat of undergrad E&M, but with green functions and contour integrals. Oh, is this for a graduate E&M course? Yeah, I don't know how much of my knowledge is lacking about E&M really, because I've never taken a graduate E&M course. But I guess it's not, I suppose beyond stuff like learning about plasmas and things, there's not a huge amount of E&M that I think would be too relevant to me. I mean, plasmas are really interesting, and I wish I knew more about plasma physics sort of rigorously. Yeah, that stuff is all really cool. So there was another question I found on Reddit where someone was asking this question, and then this question, it actually turns out, is a question from some of the MIT OpenCourseWare stuff. So it's a little mechanics problem from there, which we can talk about because it's sort of interesting. Plasmas would require fluids which physicists pretend don't exist. Well, I probably know quite a few fluid dynamicists that would disagree with that. But yeah, it's interesting, all that stuff. I think fluid dynamics is a nice part of physics because you can really sort of think about what's going on and kind of picture things. It's very sort of rich with being able to visualize things and add things on that make the problem more difficult, and it's a real kind of physicist's piece of physics. You have to think about what approximations are valid all the time, whether you can do certain things. It's very hands-on and very interesting, and it's got a lot of maths in it too, of course. You can't really do fluid dynamics properly without knowing a bit of complex analysis and stuff like that. So it's pretty cool. Find me a fluids course in the average physics program. It doesn't exist. That said, there are a lot of fluids physicists in the same program. Well, I suppose that's true. I think a lot of undergraduate universities in the UK actually don't do fluid dynamics, or if they do, it's like an option. It wasn't an option at my university anyway. We had to do it in our third year, and I'm glad we did because it wouldn't have been something I would have chosen. I definitely wouldn't have opted to do fluid mechanics, but it was a good course in the end, and it does give you an appreciation of sort of how physics is done and thinking about modelling and approximations and stuff, which is a serious skill to have. So let's talk about... Oh, sorry, I missed a message. So Justin Culp said they think graduate E&M in North America is doing ridiculous PDEs from Jackson, but that's just your impression. Oh, right, okay. Yeah, Jackson is too rich for my blood. I used, what's it called? What's the really... Griffiths. I used Griffiths E&M for my courses, and that was just fine for me. Yeah, exactly, Griffiths. Exactly. Okay, so let's look at this problem now. Feel free to, post any other things in the chat though, and I'll kind of dip in and out. And if this question just gets boring, then I'll pick up one from the chat if there is one there. So you can see the problem here. We've got something on a slope. We've got a thing undergoing circular motion on the slope. And the first thing we want to do... Oh, well, I should also say it's a rough slope, as they tell us. The slope is at some angle phi to the horizontal, and it has some coefficient of friction mu, they tell us. So it will feel a frictional force as it goes around. But then... yeah, I've heard Jackson uses that phrase, "This exercise is trivial and left for the," that kind of style of phrase quite a lot. That's probably why I've avoided that. I don't like that in textbooks. Okay, so the first thing they want us to do is to find how much work the frictional force does moving from the bottom to the top. So we're kind of firing this thing off at speed v0, and we're seeing what happens to it when it gets to the top. Well, so this first part is pretty straightforward. So the object will have some normal force N on it, and this normal force doesn't change between the top and the bottom. It doesn't change as the thing is going around, okay? The forces that are changing on this particle are only along the direction of the plane. They're not in the direction perpendicular to the plane. So the normal force is the same as this thing moves from the bottom to the top, okay? And we can work out the magnitude of that normal force, so I'll just draw it on this diagram here. So this is the vertical, and this is the line carrying on from the normal. So you can justify to yourself from trigonometry that this angle here is the same angle phi as is between the horizontal and the plane. And you can use trigonometry then to say that the normal force of the plane acting on the particle is given by mg cosine of theta, okay? Because mg is the force that is dragging the particle down in this direction, and n is the reaction force that balances that stops the particle falling through the table. So that's the magnitude of the reaction force, and you know that frictional force, which I'm going to call Fr, is given by the normal force multiplied by the coefficient of friction, or rather this is the maximum friction you can find. But of course, if the object is moving, its friction is maximal. It's only when things are in sort of limiting equilibrium that friction is not necessarily at its maximum value. So that is the force of friction, that say the particle is here, and it's moving around, it's moving tangentially to the circle with some speed v. The force F I've just drawn, the frictional force, is the force that is dragging it back, trying to slow it down along that direction. So as it moves from the bottom to the top, it moves half of the total circumference of this circle. So if you want to find the work done by this frictional force, you have to take force that is applied to the particle in the direction that it's moving, multiplied by the distance that it travels. Okay, and we don't have to integrate or anything because, as I said, the normal force is the same all the way along this circular arc. Therefore, the frictional force is the same all the way along this circular arc. So it doesn't matter. It's just n and then n mu the whole way. So that is n mu times the distance it moves, which is half of the circumference of the circle. Well, that's 2 pi r divided by 2. So that is just pi big R. Okay. You're going to lurk for a few. Okay. What was I saying? Yeah, okay. And then we're putting n that we found here, the magnitude of the normal force, back into here. Okay. So the work done, therefore, is mg mu pi r cos phi. I ran out of room a little bit. Okay. So that's the straightforward part. Theoretical phys says, what does it mean for something to be relatively trivial? I don't know. Maybe it means in one inertial reference frame it's trivial, in another it's highly non-trivial, which actually happens quite a lot, I guess, in GR. Things are pretty trivial in free-falling coordinates, but are not in other reference frames. I'm joking, that's not what it means. Anyway, part B is a little harder. So part B says, what is the tension in the string when it reaches point B? Express your answer in terms of m phi, v0g, and mu, etc. Okay, so at the top here, let's say that the particle has got some speed v as it's moving around the circle. So we can think about the centripetal forces that are the centripetal force on this object. We can think about all of the forces that are acting down the plane and up the plane, etc. So if we draw forces on this particle, we have the tension that is acting down the plane, and we have friction that is acting sort of to oppose the direction of velocity, so that doesn't change anything about the motion down the plane. And then we have the weight of the particle. So the weight is kind of in a downwards direction going into the plane. So the weight is like this, drawing it here, going vertically downwards. So if we want to find the component of the weight, mg, which is going down the slope, we have to do mg and multiply it by sine phi. So resolving down the slope, we have t plus mg sine phi is equal to what? Well, these are the forces that are providing the centripetal acceleration. So if the particle has some speed v here, and it's moving about center of rotation of radius r, then these forces all have to conspire to give mv squared over r. Okay. So the reason that we've not thought about friction here as being up the plane or down the plane is that the particle is not about to move either up the plane or down the plane. It's moving in this circle around, so at this instant here, it's moving to the right, and therefore friction is to the left. Friction opposes either the direction something is moving or the direction it's about to move in. So friction is not going to be acting up or down this plane, only to the side. It's just a comment. Well, now we need to find an expression for v, because v is not going to be the same as v0. The speed we start off here when we fire this ball up is not going to be the same as this final speed here. Because this is a friction, this is a rough plane, it's going to do work and reduce the energy of this thing. Exactly, we're using energy conservation. So we have to think about the work that is done on this particle by friction, which fortunately the question has already had us calculate. Okay? So let's think about energy conservation. Let's think about total energy at the bottom of the plane. By the bottom I mean here. Oh, well, they've labelled points A and B. So B is the top, A is the bottom. So let me call it A. That's a little more compact. So the total energy at point A is going to be, well, it has some kinetic energy. Half m v0 squared. Yep, 2r sine theta will definitely come into it. Non-dairy neutrino is... Now do it when the ramp has a radius of curvature 1 over epsilon. Yeah, that would be pretty horrible. Yeah, I mean, I guess if you had some sort of general curved bowl, you would just have to find the normal of the curve and find the magnitude of the normal by taking like the dot product of the normal vector with the weight vector, or minus that rather. That would give you the normal vector, the normal force, and then you would have to times that by the coefficient of friction and integrate that along the path you were traveling around. I suppose it's how you would start generalizing that to some kind of manifold, or just some curved surface or something. I will think about that very shortly, Exaventian. I'll just finish doing this. And theoretical phys 77 is totally right. I am going to use 2r sine theta when I come to find the potential energy. Okay. So anyway, the energy at the bottom, well, if I measure the potential energy from the bottom here, so I take this as being 0 potential, and this as being some height above, which will have potential energy, I can then calculate... Oh yeah, good idea. Thank you for clicking the Discord thing. Please do join the Discord. I can find the height that this thing will go to, and therefore I can find the potential energy it has at the top. So the total energy at point B is going to be, well, it still has kinetic energy. As I've drawn it here, it still has some velocity. So it still has half mv squared, not v naught squared, v squared, as kinetic energy. And now it has some additional height, which we need to calculate, as that will affect the potential energy. So the potential energy is mg times the height that it is raised up, which theoretical phys rightly said, if you sort of draw this side on, it goes from this point A here to B here. This length here, the hypotenuse of this triangle, has length 2r. This whole thing has angle, oops, not theta, angle phi. So finding the height h is just from trigonometry, it's hypotenuse times sine phi. So that is 2r sine phi. Okay. And now we can use conservation of energy to find this final velocity. So we can't just set E total at A equal to E total at B, because we have lost some energy. We've calculated that friction has taken energy out of this system. It's done work on this particle as it goes around. So whatever energy the particle has here, that has been taken away in part by the frictional force as it moves around. So to put that into an equation, we can say that the energy, the total energy at A, minus the work done by friction, is equal to the total energy at B. And of course we have our expression for W, for the work done, which I will copy because my memory is like a goldfish, so I will forget it. So we can say ET at A minus this is equal to ET at B. And now we have expressions for ET at A and ET at B, so we can start rearranging to find v squared here, the final speed. So ET at B is just ET at A minus this thing, and now from the ET at B we want to get rid of this term here, so we're going to also subtract from both sides mg2r sine theta. So in part then we can write down half mv squared is equal to half m v naught squared minus mg mu pi r cos phi, Sleyadarth is back, hello, minus this term here, which I'm now taking the 2 out the front. So that is 2mg r sine phi. Okay, so this expression will tell us the final velocity of the particle when it gets to the top of the ramp up here. And remember, it's the tension we're trying to find, so we've written down our equation for the tension here, as you can see. So now we're just combining this equation with this equation, and we can quite straightforwardly write down an expression for the tension. So from here, the tension is given by mv squared over r minus, not in red, minus mg sine theta. And now we just want to sub in for v squared or for mv squared in this top thing up here. So putting that all together, I just multiply both sides of this equation by 2 to turn it into mv squared. So I have t is equal to, well, of course, I also need to divide by r is crucial. This is all mv squared over r. So I have mv naught squared over R minus 2 mg mu pi cos phi, where this R here is cancelled by dividing by this R, minus 4 mg sine phi. Okay, and of course I also need this expression here, this minus mg sine phi. And that was from the tension equation. So we can simplify this down now a little bit. This whole thing is equal to mv naught squared over r minus, and now I'd like to take an mg out of here just to make things look a little nicer. Minus mg, and now I can simplify this a little bit too. So I have a minus 4mg and a minus mg, so that gives me in total a 5 sine phi. And here I write this all as plus 2 pi mu, I'll keep the pi with it, cos phi. So that's the expression I get for the final tension at the top of this thing. Now, if you spotted any errors, or feel free to go back and watch this and see if you spot any errors, do just let me know, because I did make a couple of slight errors just in sort of the end stages of a calculation on one I did last time. But it didn't actually change the overall answer. It was just I sketched a cosine squared curve wrong, and I did an integral thingy slightly wrong too. Am I going to do the Sandbox Sunday thing? I am. I actually changed it. I'm actually going to do it on Saturday though, not on Sunday, because I realised the time I wanted to do it, I didn't want to interrupt when Physics O is also streaming on Sunday. So on Sunday, if you're looking for something to do, definitely go and check out Physics O streaming. I think he starts at 6 p.m. UK time. It might be 7 p.m. UK time. I can't actually remember, but do go and follow him and take a look. But yeah, I am going to do that on Saturday. So this Saturday, we're going to. So what I'm thinking about doing, for those of you that weren't here when I mentioned this the other day, is doing something I'm going to call Saturday Spacewalk. Now, it's a good thing that both days on the weekend start with an S, isn't it? Where I'm going to play on Universe Sandbox a little bit. So we're just going to sort of walk around the solar system a little and talk about a few different planets. And we're going to try and do them in order and talk a little bit about something specific about all of them. Now, this obviously won't all be in one go. This weekend probably we'll just talk about Mercury. And particularly about Mercury, I want to talk about orbits in general of planets. And I want to work through a result that comes from general relativity. So I will go through the general relativity side of it, but if you haven't seen general relativity before, you can still come along and look at it, because I'll try and relate it back to the Newtonian approach to things anyway. Although you do need general relativity to get this. But the point is I'll try and derive what's called the orbital precession of Mercury from general relativity. So this comes about as a higher order term that affects the gravitational potential that Mercury feels from the Sun. So you can think about it, if you only know classical mechanics and you don't know general relativity, you can think of it just as I'm adding a term to the potential that Mercury feels, and then from that we'll derive the angle by which Mercury's orbit changes each year, and maybe we'll talk a bit about how this was one of the first sort of experimental proofs of general relativity, and try and relate it to some actual data if we can. And we'll just sort of take a walk around and look at Mercury, because Universe Sandbox is quite pretty anyway. So we'll see that, and we'll talk about some properties of the planet too. And then we'll go through the other planets sort of after that as we go. But yeah, I'll do a post about that somewhere after this and try and mention it. A non-dairy neutrino has done that exactly, but computationally. Yeah, so you can do it okay computationally. You can solve it pretty exactly. Can you solve it exactly? I actually can't remember. I'll have to do the calculation beforehand to remind myself, of course. But I seem to remember solving it exactly, completely analytically before. Then Theoretical Phys 77 says, are there any notes/books you recommend to read up on GR before Saturday? Well, I think you'd be a bit pushed, if you've never studied general relativity, you'd be a little bit pushed to learn general relativity by Saturday. It is pretty difficult. But as general resources, Sean Carroll's book I think is quite good. But it's quite good as a certain sort of approach, I think. If you want to know about, you know, tangent vectors and tangent planes and stuff, then that's quite nice. And he has quite a lot of detail, but also a lot of intuitive stuff. Wold. Yeah, don't read Wold by Saturday. Yeah, what was I saying? Some other GR notes. I'm not sure actually. Carroll is probably one of the best GR books as a first read. Now I think about it. Well, there's a good one that's by Cambridge University Press that is. Oh, what's it called? Who is it by? It's just called a first course, or it's called an Introduction to General Relativity. Who is it by though? It is by. No. Oh, well, actually, Hobson is quite good for general relativity too. But where is this other one? I think it is Schutz actually. Schutz, however you say it. It's got, and all I know is it's got like a blue front cover with like water drops on the front. That is the one I remember. I think it's that one. Funnily enough, I got that book. Yeah, it is Bernard Schutz. That's it. That's a good book. That was the first GR book I read. I got that book, funnily enough, I think for my 16th birthday or something, thinking I could try and learn GR as like a 16-year-old. And well, obviously I didn't actually read it. I also got the same birthday, I think, I asked for this book when I was 16. A first course in string theory. It's actually a really good book and it is really accessible, but it was stupid asking for it when I was 16. I think I didn't realise at that point just how much maths physics had in it. But yeah, there are lots of quite good GR resources. Schutz is good. Carroll is good. I find if you want to look for Zweibach, he's the guy at MIT. I think if you're looking for GR, there are some really good lectures online you can find actually. So Susskind does some pretty good GR lectures, where I'll be honest, I've never watched past the first lecture. I tend to watch the first lecture for all of those ones that Susskind does, and think, oh, this is great, and then never get back to it. But I guess if you've never learnt GR before, maybe you'll be more motivated to stick with it. But yeah, that's pretty good, and his first lecture gives a nice sort of intuitive explanation of stuff like the equivalence principle, and it's a great thing. He does meander a lot. He really does meander a lot. But I think, those meandering are usually quite insightful. With a guy like him, any sort of offhand bit of information is probably worth something, and probably worth attention. They are long, that's right. There's definitely ways to learn it quicker. Yeah, and he's always munching on cookies. Yeah, that's true. But yeah, there are lots of good things for GR. But I wouldn't worry about what is Hobson? That is Hobson. There are two other guys too. It's just called General Relativity, an Introduction for Physicists. Hobson, Lassenby, and I can't say the name. I'm really bad at doing those names. So, well, Carroll's book actually, Carroll's book springs from a set of lecture notes that he, lectured at Caltech, and the lecture notes that are pretty much the same as the book is still available free online. So you can download the lecture notes that the book is heavily based on online and read those, without buying the book. I mean, I know there are ways of getting the book without buying the book, but if you wanted to be totally honest, you can just read the lecture notes without having to do that. But yeah, so that's what I'll do next time. Well, not next time, on Saturday. And yeah, lecture notes on archive, like PhysicsO says, there are lots of them that are really good. And yeah, people post them for free. So those are a good idea to take a look at. Well, so it's pretty much 8 o'clock, so I'll get ready to say goodbye. Feel free, if you haven't already, what I'll do is I'll post this video. I'll upload this on YouTube in case anyone missed it, although obviously by the definition of being here you haven't missed it, but maybe you missed the start. So if you click my about, you can go to the YouTube page and watch some previous ramblings. You can follow me on Twitter if you like. Join my Discord would actually be pretty cool. Oh yeah, thank you, Jigchin, for doing the Discord. And yeah, I will see some of you on, what day is it? On Thursday, where we'll do Mario Kart and physics chat. So feel free to come along. You can chat about physics then. Oh, someone said, thoughts on the impact of 12.5-year dataset on nanograph PTAs? I don't actually know a lot about that, I'm afraid. There's not something I know about. Yeah, apologies. Maybe come and give some more details on Thursday, and we can chat about it then. Sorry, I think didn't get around to answering that properly. Oh yeah, can we raid? Who should we raid? Tell me who to raid. There is Prof Melko is streaming at the moment. Oh, no problem. Thank you, Quark Chum. Why don't we go and raid Prof Melko? Let's do that. Oh, wait, how do I do it again? /raid. He has raids turned off. Oh, well. What's the point then? Okay, what about not prof? Does not prof have raids on? I mean, we can just raid him quickly. We don't have to interrupt him doing anything. Let's try and raid not prof. Okay, let's get ready.